So he's putting masses on, and it's always his choice. I mean, it's what you say. How did he come to that conclusion? So we've had all kinds of different masses he's used on pendulums. He has them, round, bally things, this, that. Now he's using hollow washers that have a terrible profile, frankly. Their center of mass isn't very centered. There's a whole bunch of mass out here and a whole bunch of mass out here, which is far from the ideal. You want the mass to be as concentrated as possible, presumably. Because then he tapes washers. Okay, this time I'm gonna have the experiment done right. I'm gonna actually have the masses connected. Not freely flying around, bouncing around on the lever.
Wow, just look at how much the masses are bouncing around while they go through the timing gate.
But the problem with that is you have to make sure which way are you going to, if it tapes the washer this way, right, you can understand that, the center of mass isn't in the center anymore.
Okay, so the problem was, since the hole, the diameter, right, is bigger than the diameter of the bar. So which means now the mass is hanging, the center of mass is a little bit below the bar. Oh yeah. So ideally it should have been like this. Instead of this. Can you see that? Instead of this should be like this, a bit higher. It's a difference of a couple of millimeters. So that's how I manipulate my results. That's the way I did it, right? Alright, now let's use another mass. The diameter of this hole is pretty much identical to the diameter of the tube. It's only, I don't know, 1 or 2 millimeters in difference. Alright, so look at that. Would that be good? Let's try it out. It's also a really thin mass.
We've been over and over and over, it's a sensible release system for putting the energy in. And so he makes a lever and then he puts a stop halfway here, and then he pulls on it here. And you're saying, well, wouldn't it make more sense to pull on it right at the stop? Because then you can't bend it. You can't put extra pressure on it. You can't do any of that. There's no possibility of bending it. So this is his own invention, do a loop of string and then just cut it. So he could do that, but he didn't bother.
Alright, this is the one mass at the 4 distance mark. I'm going to release it closer to the fulcrum. This is the fulcrum. This is the release point. Instead of here, I'm releasing it from here. And also with a quick release, I'm going to cut the string with the scissor. Here we go. 100. Alright. Trial 2. 94, let me show you. 94. Trial 3. 95. 95. Okay, trial 4. 94. 94. Okay, let's measure the distance of the one mass. So here's the fulcrum, 0 centimeters. The one mass is located at 47.5 centimeters. Yes, 47.5. Okay, now the distance of the two mass. So that should be around 23.75. Can you see that? It looks more or less. I can't go lower. Hold on. No, I can't go lower. So this is around 23.7. All right, now the two mass at the two distance. Trial 1. Dear. 71. Oh no, it goes faster again. God damn it. Two mass trial 2. God, once again. I'm probably manipulating the things again. What the hell? Two mass trial 3. Yo, what the hell's going on, man? How can this be possible? It's going faster each time than one mass further out. Whew, what the fuck's going on here? Is this magic? Okay, so this should be the point at which the two mass has the same angular speed as the one mass at 4 times the distance. There we go. 96. Okay, trial 2. 94. Here we go. Alright, so let's measure the distance now. Okay, here we go. That is around 31 and a half. 47 and a half divided by 31 and a half equals 1.5. So ideally it should have been around 1.41. It's 1.5.
How long are you going to persevere in your denialism? What you claim should happen literally never happens. Never, never, Gary. Absolutely never.
Never! Never! Never!